Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today, we're going to shift focus a little bit from the propositional calculus that we've been going through to look at Boolean algebra. And we'll start with a discussion of Boolean functions. It won't take you very long to see that there is a clear connection between propositional calculus and Boolean algebra. In this topic, we're going to think of 0 as corresponding to false and 1 as corresponding to true. Now, the complement of elements of the set 0 and 1 are defined as follows. The complement of 0 is 1. In other words, the opposite of false is true. The negation of false is true. The complement of 1 is 0. The negation of true is false. And that's literally how we're thinking about these two expressions. The complement of false is true. The negation of false is true. The negation of true is false. We're going to define the Boolean sum by 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1, and 1 plus 1 is 1. We're thinking of this as the OR statement instead of plus. So true or true is true. True or false is true. False or true is true, and false or false is still false. So that's one way to view this Boolean sum. We also have the Boolean product. If the Boolean sum acted like OR, the Boolean product acts like AND. So here, 0 times 0 is 0. False and false is false. 0 times 1 is 0. False and true is still false because they have to both be true to be true as an AND statement. 1 times 0 is, of course, 0, and 1 times 1 is 1. So here we're thinking of the product as being like an AND. Do you see how nicely this Boolean arithmetic fits with our propositional calculus? It's a direct correspondence, but we need an order of operations. In particular, the complement has highest precedence. So in any expression, complement goes first, of course parentheses perhaps on top of that. Then we have products, and then sums. So for example, suppose we have 0 times 1 in parentheses and the complement of that plus 0 plus 1. What do you get? Remember, this is an OR statement, so 0 plus 1 will be 1. 0 times 1 is 0. So we'll have 0 complement plus 1. Well, the complement of 0 is 1, and that has to go before the plus. And then 1 plus 1, 1 or 1, is 1. To translate this whole computation back to the propositional variables, we would have not false and true, or false or true. Well, we know false and true is false, and so we'll say not false. Or, over here we'll have false or true, which is true. Not false is true, and true or true is still true. As another example, let's suppose that we have true and false, or not false. Notice that true and false is false, but not false is true, false or true is still true. Now, let's convert this into zeros and ones in our Boolean algebra. Here we have one, since this is an and, it's a times, 0. Or is plus, and this is the complement of false, so the complement of false. You can see 1 times 0 is 0, and the complement of 0 is 1. 0 plus 1 is 1, yielding true. It's kind of remarkable that we can do logic with numbers 0 and 1 using this Boolean arithmetic. As you can see, this makes it possible to prove expressions using computers, zeros and ones. Next, some notation. We'll set B to be the set 0 and 1. So what is B squared, or B cross B? This is the set of all ordered pairs, A and B, such that A and B are elements of the set B. If that's the case, what's B3? Well, it's obviously the set of all ordered triples. And we can even generalize beyond this. We can go to ordered 4 tuples, or 5 tuples, or 6 tuples, and so on. More generally, Bn is the set of ordered n tuples. Let's write this as x1, x2 through xn, such that each of these x sub k's come from the set B. K will go from 1 to n. We call x a Boolean variable if it only takes values in B, namely 0 or 1. A function from Bn into B is called a Boolean function of degree n. Let me give you an example of a Boolean function. Suppose this function has 2 Boolean variables, and it's defined to be x times y complement. Here, we're using the principle that if we set 2 variables next to each other, that is, if they are juxtaposed, then we're implying that they are multiplied, and in this case, using Boolean multiplication. So we can actually make a kind of truth table for this function. For the first column here, we'll write 1, 1, 0, 0, true, true, false, false, and then true, false, true, false, 1, 0, 1, 0. The complement of y is 0, 1, 0, 1, and then the times, remember, is an AND condition. So multiplying these two columns here, we'll have 0, 1, 0, 0. As another example, look at f of xy equals x complement plus y. xy, we'll need an x complement and then x complement plus y. For the x column, it'll be 1, 1, 0, 0 for true, true, false, false. And for the y column, 1, 0, 1, 0. The x complement will be 0, 0, 1, 1. And then the plus is an OR statement. So only one of these needs to be a 1 to put a 1 here. So we have 1, 0, 1, 1. Note that this corresponds to not x, and the plus is an OR y. And that corresponds to x implies y. So you can see these Boolean expressions correspond very nicely to propositions. Next, we're going to look at Boolean expressions defined recursively. Of course, we always start off with 0 and 1. We can have Boolean variables x1, x2, xn. If e1 and e2 are Boolean expressions, then so are e1 complement, e1 plus e2, e1 times e2. So we can combine Boolean expressions to make more complicated Boolean expressions. There's a concept called n-cubes for Boolean functions. So to explore this, I'd like to go back to the Boolean function that we've looked at just a moment ago, x bar plus y. Now we had the table x, y, x bar plus y, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, and then the OR statement 1, and then the OR statement between these two columns, which is 1, 0, 1, 1. And we mentioned that this corresponds nicely to the proposition x implies y. Now, think about this as these as ordered pairs going into our function. We have 1, 1 that goes in. That's a point on the graph here. 1, 0. We also have the point 0, 1 and the point 0, 0. Let's connect these all with line segments. Then, everywhere we see a 1 in this table over here, we will shade that vertex. The only one that doesn't get shaded is 1, 0. And so it's left just as a corner like this. This is our n-cube, in this case a 2 cube, for the Boolean function x complement plus y. So how in general do you make the n-cube? You have your independent Boolean variables, x, y, z, however many variables you have. If you only have 2 variables, you get a 2-dimensional object, in this case a square. With 3, though, you'll get the vertices of a cube in 3 space. If you have 4 Boolean variables, you'll have to draw that in 4 dimensions, so that'll be a little tough. But nonetheless, after you have plotted the vertices for the Boolean function, you then shade the corners that correspond to true, or 1, and as a shaded dot, like this. For another example, suppose we have the Boolean function f of xyz equals xy plus z complement. What will the n cube look like in this case? Well, we're going to need to have our table. We're going to need z complement xy and then xy plus z complement. Since there are 3 variables, we'll have to have 1, 1, 1, 1, 0, 0, 0, 0. 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. Z complement will be 0, 1, 0, 1, 0, 1, 0, 1. X times y is the AND statement, so you'll get 1, 1, 0, 0, 0, 0, 0, and 0. Finally, we'll add these 2 columns here, and that's an OR statement, so you'll get 1, 1, 0, 1, 0, 1, 0, 1. So for our 3 cube, we'll have vertices 0, 0, 0. Moving 1 over here, it'll be 1, 0, 0. If you move 1 back, that's 0, 1, 0. And if you move 1 up, that's 0, 0, 1. We're going to have corners connected something like this. So this corner back here will be 1, 1, 0. This will be 1, 1, 1. We have this corner here. The corner back here is going to be 0, 1, 1. And then the only one missing is the corner right here, and that's going to be 1, 1, 1, 0, 1. So which of these corners get shaded? Well, 1, 1, 1 is true, so that'll be shaded. 1, 1, 0 is also true. 1, 1, 0 gets shaded. 1, 0, 1 is in the back here. It's false, so it does not get shaded. 1, 0, 0 is right here. That's a true, so it gets shaded. 0, 1, 1. 1, 1, 0 is true, but 0, 1, 1 is false. So I made an error here. Yeah, 1, 1, 0 is over here. That's true. But 0, 1, 1 is false. 0, 1, 0 is true. 0, 0, 1, 0, 0, 1 is false, and 0, 0, 0 is true. So only these 3 corners do not get shaded in the 3 cube in this case. How do you know whether or not 2 Boolean functions are equal? Well, as long as they have all the same values for all the same inputs. We say that f and g of the same degree are equal, and write f equals g, if they have the same values For all of these bk's, taking their values in b, which are zeros and ones, and k running from 1 to n. That's what it means for these two functions to be equal. Different Boolean expressions that represent the same Boolean function are called equivalent. Go figure. As an easy example, xy plus 0 is equivalent to xy times 1. The complement of a Boolean function f is denoted by f complement. Since you can take the complement of the function, you can also add them and multiply them. These are defined in fairly obvious ways. If you have f of b1, b2, all the way through bn, if you add that to g of b1, b2, all the way to bn, what you get is f plus g evaluated at b1, b2, all the way to bn, and so on. So it's easy to define these. How do you add two functions together? Well, you just add them. So if I have f of xy equals x complement y and g of xy equals x plus y, then f plus g of xy will be x complement y plus x plus y. Now, since Boolean functions have variables that only take on values 0 and 1, and Boolean functions only output values of 0 or 1, depending upon the values of the inputs, there are only a finite number of Boolean functions of each degree. So if I have a Boolean function of degree 2, so I have two Boolean variables x and y, each x and y can take on two different values, and the output can take on only two different values. So for each of these points, how many points are there in the domain? The domain is b2. For this Boolean function. How many elements are there in b2? Well, you have 0, 0, 0, 1, 1, 0, and 1, 1. You have two spots to fill, two things to fill each spot. That gives you 4 different possibilities. Each of these 4 possibilities is assigned to a value either 0 or 1. So these 4 possibilities represent 4 spaces that you can fill with 2 possible values. That gives you 16 possible Boolean functions of degree 2. If the cardinality of a set is the number of its elements, the cardinality of B2 is 4. So, how many Boolean functions are there of degree 2? 2 to the cardinality of B2, 2 to the power of 4, which is 16. So how many Boolean functions are there of degree 3? Well, the cardinality of B3 is 8. You have 3 spots to fill with 2 possibilities. So the number of Boolean functions will be 2 to the power of 8. Well, that's 256. So there are 256 possible Boolean functions of degree 3. And that's how you would calculate it more generally. More generally, there are 2 to the 2 to the n Boolean functions of degree n. Now, predicate logic had a lot of identities, and so Boolean algebra will also have a lot of identities. An easy one would be x complement complement. That's a double negation, which just leaves x. We can call this the law of double complement. There are also idempotent laws. It turns out that x plus x equals x. This is an or statement. So x is true or x is true gives you true. False or false gives you false. So you may as well just go with x. And there's another idempotent law. X times x is x. So there's really no point in having things like x squared in your Boolean functional expressions or Boolean expressions more generally, because x squared is equal to x. This is an and statement. True and true is true. False and false is false. So those are your idempotent identities. And of course there are certain identity laws. X plus 0 is x. Right, so if this is true or false, still true. False or false is still false. So 0 acts like the additive identity from real numbers in that sense. What about x times 1? This is an and statement, so true and true will be true. False and true will be false. So these are the identity laws, idempotent laws, double negation. We have the domination laws. X plus 1 is 1. X times 0 is 0. Yes, if this is an and statement and you already have one of the factors false, you get false no matter what the value of x is. And if this is an or statement and one of the values is already true, you get true no matter what the value of x is. We have, of course, the commutative and associative laws. X plus y is y plus x. X times y is y times x. These are your commutative laws. The terms commute, they move around. And we said there are associative laws. X plus y plus z will be the same thing as x plus y plus z. X times y times z will be the same thing as x times y times z. So these are your associative laws, where you're associating different terms or factors in these expressions. Then there are, of course, distributive laws. X times y plus z will be x times y plus x times z. We also have De Morgan's laws. What if we have x times y complement? That'll be x complement plus y complement. Notice how this refers back to not x and y equals not x or not y. So here's the or statement, there's your and statement. In addition, if we have x plus y complement, that's the same thing as x complement times y complement. We also have absorption laws. X plus x times y. Well, if this is an and statement, then x must be true and y is true here. But this is an or statement, so whether this is true or false, if this is true, it'll be true. If this is false, then x is false, so the and statement will be false as well. You may as well just say false. So x plus x times y simplifies to just x. Similarly, suppose you have x times x plus y. The only way this is going to be a true value on the other side is if both x is true and x or y is true. But if you already know x is true, why not just say x? If x is false, then the whole thing is false, and so you may as well just write false. So here, you can kind of think of this as x squared plus xy, but x squared is x, as we've demonstrated already. X times x is x by the idempotency laws. And then we already know from above that this expression yields only x. So we get these two absorption laws. So you can simplify expressions using these principles. For property 10, consider x plus x complement. Variable x or the negation of x. It has to be true no matter what x is. If x is true, you get 1. If x is 0, then x complement is 1, in which case you still get 1. So in all cases, for any value of x, you'll get 1. We'll call this the unit property. And finally, x times x complement has to be 0 no matter what. This is an and. If x is true, then x complement is false, so the and will be false. If x is false, then x complement is true, but it's still false, so you still get 0 in all cases. We can call this the 0 property. The dual of a Boolean expression is obtained by swapping pluses and timeses and also zeros and 1s. For example, x plus y times 1. Its dual is x times y plus 0. As another example of the dual of a Boolean expression, suppose we have x times x plus y. The dual will be x plus x times y. Notice that this simplifies to just x, but this also simplifies to merely x. More generally, we can talk about Boolean algebras. So what is an abstract Boolean algebra? It's a set B with, it could have more than 2 elements, with at least elements corresponding to 0 and 1. We must have operations and or. In the Boolean algebra that we've seen so far, that would be times and plus. And a complement operation. X complement. To qualify as a Boolean algebra, this set and these operations must also satisfy certain basic properties. So for instance, x or 0 will be x. That's an identity law. X and 1 will be x. So this is the additive identity. This is the multiplicative identity. 2, x or x bar will be true no matter what. It'll be 1. Takes the value of 1. Also, x and x complement will have to take the value of 0. We must have commutative and associative laws. So for both of the operations, and or, plus and times, both must be commutative so you can commute the terms around, and associative so you can regroup and get the same thing. And finally, you must have distributive laws. So that x or y and z will be x or y and x or z, where we're distributing the disjunction over the conjunction here. And it has to go the other way around too. X and y or z equals x and y or x and z. So any set that satisfies all of these operations, all of these conditions, will be called a Boolean algebra. Now, obviously, sets where b is 0 and 1, and we've defined and to be times and or to be plus as we have, gives you an example of a Boolean algebra, but there are others. As an example, let me first define what I mean by the power set of a set. So let S be a set. Its power set is denoted by a fancy P of S and is defined as the set of all subsets of S. So for example, if my set S is the set 0, 1, 2, then the power set of S will be the set of all subsets, which includes the empty set, the set that contains 0, the set that contains 1, the set that contains 2, the set that contains 0 and 1, the set that contains 0 and 2, the set that contains 1 and 2, and the set that contains 0, 1, and 2. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible subsets of this original set that has 3 elements. By the way, if a set has n elements, if the cardinality of a set is n, then the number of elements in the power set will be 2 to the power n. So here we have 2 to the power 3 equals 8. We expect 8 elements in the power set. You can then define a Boolean algebra on the power set of an arbitrary set S. How do you do it? The operations are intersection for and union for or, and then complement for complement. So the complement of a set, let's suppose my set S is 0, 1, 2, and I have a set A which is 0, 2, then the complement of A will be everything in S that isn't in A. namely 1. The interesting point to note is that results for Boolean algebras apply clearly to sets, but also to propositions, and even Boolean expressions. So Boolean algebras form kind of a meta-theory that applies to all of these things.